Hey guys, welcome back to the channel. Today we are doing what I will call a buzzer beater video because I'm hoping to just get it off in time before it gets dark and my recording looks bad. Similarly, I just took a buzzer beater poop. That one had nothing to do with the daylight. You guys can interpret it yourself. So I was inspired to make this video by another good systems design channel, Systems Design Fight Club. That being said, I do think that while I agreed with what he did say for the most part, maybe I felt that he was missing, I don't know, like a good quarter of the details for the problem, and so I was hoping to amend onto this problem myself and maybe make it a little bit more concise. Anyways, hope you guys enjoy. Alrighty, so let's go ahead and get into things. Basically, today's video is going to be about searching your mutual connections on LinkedIn. So if you guys are LinkedIn users, you will know that if you use the search bar, there's an option to basically check for your first connections, so people you're directly connected with, but then there's also an option to actually search for certain criteria for people that you're mutually connected with. So for example, you can search mutual connections with a given school or a given current job. In this case, obviously, we've got people who come up that I'm mutually connected with, who went to Hustlers University and are OnlyFans creators. We can see that's Korinikoff and Trump. So let's go ahead and formalize this problem requirement. Basically, the gist is we want to be able to search our LinkedIn for connections where basically it's going to be specifically a mutual connection, right? So if this is me, I have some sort of connection. I'm going to omit connection search in this problem because that's, go to a database and search it based on all my connections. The mutual connection is one where I'm not actually connected to them, but we share a connection in common. So this is going to be a pretty interesting problem. Another thing that I'm going to omit from it is actually not a full text search. If we did want to do a full text search, it would just be putting everything in a search index, which we know how to do. But to keep things simple for now, I'm just going to say, hey, let's search by like a hard-coded string for basically your education or your current employer. So I'm just going to imagine those are fields in a database, and we're just going to be using like an education equals Cornell University, for example, or something like that. Cool, so I am actually going to do capacity estimates here because it's going to become pretty relevant for a problem like this. We'll see why that is mainly later. I'm going to assume that we've got 1 billion users on the site. That's pretty big to assume that 1/8 of the world is on LinkedIn. May be true, may not be true, but I think that's pretty realistic for something like this. I also think that on average, having each user with 500 connections is pretty reasonable. Now, to be fair, I am not going to discuss very much in this video what it would be like if a particular user has a lot more than 500 connections. LinkedIn does cap it at some point, but I'm not sure of the exact number, and it's definitely higher than 500. That being said, they do stop showing the number at 500, so it's hard for me to say exactly. This problem would be pretty interesting if you could have, 50,000 connections each. It would actually be quite a bit harder, and you'll see why in a little bit. So what this means is that on average, each user basically has 25,000 mutual connections, right? Because each of your 500 connections also has 500 connections. Now, it's true that we can have some overlap there, but that's why I say something like on average. Cool. Each search preview, so when we show a search preview when doing our actual search over here, we're not showing their full profile, we're just showing a few fields about them. So I'm going to assume that that contains around 1 kilobyte of data, which I think if anything is probably more than it actually is, but again, let's make this problem as hard as we can for ourselves. And also my last assumption is that each user is going to update their education or their current employer on average once per year. So if we have 1 billion users, that means we've got 1 billion updates per year, meaning that we've got around 3 million updates per day. This is all going to be relevant in a little bit. Cool. So the first thing that I want to discuss is basically the paradigm of thinking of this problem as a graph problem. So let's imagine you're right here. Your mutual connections are anyone who is basically a second-degree edge from you, but isn't also a first-degree edge, right? So, like for example, if I drew an edge between me and this guy over here, he's my connection, he's also my mutual connection, but he doesn't really count as a mutual connection. For this problem, we're going to assume that he's just a connection, right? So basically, we would be looking for all nodes at a distance of 2 connections from you, and basically this doesn't include the ones that are reached in one edge. So really the way that we would do this is just by running a depth first search. You would stop after you've reached a recursion depth of 2, and then you could use some shared hash map in that depth first search that basically allows you to see whether you've touched a given node or not. So that's simple enough. I guess the question now is what technology would we actually use in practice to do something like this? Well, perhaps we would use something like a graph database. Now, I've talked about these plenty on the channel, but just for a quick refresher, basically there are 2 types of graph databases. There's the non-native ones, Think of this as like a SQL table where you have one table solely devoted to the edges between two nodes in the graph. So in this case, we could call that a connections table, right? And what this is saying is, hey, there's an edge between user 2 and user 3. There's an edge between user 2 and user 6. There's an edge between user 3 and user 2, and so on and so on. And because we can put an index on this first column, now I can say if I want to do some sort of traversal, okay, well first I can jump to user 3. Let me now go find user 3 in this index. Oh, he's over here. Oh, now we're jumping to user 12. Let me go find user 12 in this index. Oh, he's over here. Now the problem with that is as this connections table gets bigger, because we're using an index here, what it effectively means is that we're binary searching this connections table in order to find our next node. And so that means that as the connections table gets bigger, that binary search takes longer and longer. In fact, it grows in logarithmic time relative to the number of connections. So that's why non-native graph databases handle graph data sets pretty slow. On the contrary, native graph databases will actually traverse edges in O of 1, the reason being that for a given person or a given node over here, I can actually put the physical location on disk of who they're connected to. So now basically this pointer is going to point me to user 3 on disk. User 3 has a pointer that's going to point me back to user 2, and so on and so on and so on. Now that's not to say that this is going to be particularly fast. Even if a native graph database is going to be faster than a non-native one, the problem there is that at the end of the day, we're still doing a ton of random seeks on disk, right? Hard drives are typically meant to be accessing contiguous data where we have good spatial locality. However, when we're jumping around like this all the time, it is still going to be pretty slow. As if that wasn't issue enough, however, we have another, which is going to be partitioning, right? So ideally, when we're making a query to a database, we want to typically write to one partition and we want to read to one partition. So it'd be great if we had some sort of linked-in connection graph that looked like this, right? Where we've got one cluster of people who are all interconnected. However, then we also have another cluster of people that are all interconnected, but they don't relate to one another, and then we can separate them on different partitions. This would be nice because say I wanted to find all the mutual connections of this guy right here, I only have to look at this partition. I know there's no chance that I also have to read this partition. However, in reality, the LinkedIn social graph is probably highly connected, right? In reality, we can see that it's very intertwined over here, and there's not really any good way to split it up, such that if I want to find the mutual connections for this guy, I can only read one partition. Now that is going to be a problem. Like I mentioned, we're super interconnected, so it's hard to partition well because there's no clear place to basically split out our partitions. So now, all of a sudden, if I make a connection, right, in my database, let's say I want to connect this guy here to this guy here, and they're on different partitions, now I basically have to make an edge on both of those partitions. It has to involve a two-phase commit and some sort of lock, and that is going to be problematic. And especially if I want to basically find, let's say I have another partition over here, and this guy is connected over here, and these guys are connected. Now I have to potentially read multiple partitions to find all of my guy over here's mutual connections. And so that is going to get very annoying. It's going to get very slow. It's going to get even slower if we want consistent reads from every single partition, because then we probably have to grab locks on many of those different nodes. But that's a topic for a whole different discussion. Cool, so what can we do instead? Because the graph database likely is not going to be too feasible for us here. Well, what we could do is actually basically just cache every single results for all of our users. Also, I'm very sorry that I keep fat fingering the screen today. I don't know what's happening. So we want to keep our reads as fast as possible. And the only way to basically do that is to pre-organize for every single user all of their mutual connections. Now this is an arduous process because it means that we basically have to say every single time there's a connection, load all of the user's new mutual connections. So we basically have to do a bunch of fan out, but we'll talk about that in a second. So let's say there's 1 billion users. Each one of them has 25,000 mutual connections, and each one of those kind of rows takes 1 kilobyte to store. We have to store 25 petabytes of data. Now that is objectively a pretty obscene amount of data. It is storable. There are many companies of LinkedIn size that do things like this, but it means we're going to need a lot of partitions. So the question is, how should we partition this thing? Well, we should probably shard by our user ID, right? Because for one user ID, I basically want to know, hey, who are all these mutual connections that they have, and access them all on just one database, because what we really care about here is making this read path as fast as humanly possible. And so the way that we can also do this as well is by denormalizing the profile data per mutual connection, right? It's not enough to just say, hey, this guy is user ID 4, this guy is user ID 6, and this guy is user ID 8. Because the actual profile for data for all three of these guys could live on a bunch of different database nodes, and then we find ourselves doing a large distributed join and a scatter-gather query, and that's probably going to be too expensive. So ideally, instead of doing that, what we want are our actual connection names. We've got person A, who went to school A, and works at company A, and so on and so on and so on, and denormalize that quite a bit. So of course, that is going to complicate things too. So let's actually look at how our mutual cache table might look like. I started to touch upon this a second ago. So ideally, we've got the following schema. We've got our user ID, right? So this is a user who we want to fetch all of their mutual connections for. We've got all of their mutual connection IDs. So for user ID 3 over here, we can see that they have a mutual connection of number 7, and user 10. And again, because we're denormalizing data, we can actually store their name, their school, and their company. So that's what we've gone ahead and done. In order to quickly find all of these for a given user, ideally we want to be indexed on our user ID. Another thing that we could do is within that actual user ID index, we could come up with a couple of secondary indexes, particularly local ones, because global ones can get very expensive on writes. But we can do local secondary indices on things like the name, the school, and the company, so that we can quickly find those when we're querying for them, right? If I want to query for all results for user ID 3, where one of their mutual connections went to Harvard, having an index field on the school is going to make that a lot simpler and quite a bit faster, because now I can binary search. Great. In terms of the database choice, I just went ahead and said let's use a SQL database. We don't really care if the writes to this thing are fast. We're optimizing for our read path. And so again, it's going to be nice to have a B+ tree. It's going to be nice to be able to read from a single node, as opposed to using something like Cassandra, where we might have quorum consistency and then have to read from multiple nodes at once. Cool. So what does it actually look like now when we add a connection? Because this is where things get complicated. Well, basically, let's say we've got a user over here, and he connects with a new person, right? So let's say this is user 10, and he accepts a connection from user 15, right? So now we have 10, 15. Now this piece over here, this first piece is optional, but you could have some sort of like connections ledger database just to perform change data capture on, or you could cancel that out and just throw it right in Kafka, which is ultimately what I'm going to do at the end. But the point is, we're putting the entry 10, 15 in Kafka, right? We've got some new connection. Now the first thing that's going to happen is we're going to receive this by a stateless consumer. Now note that I technically need to add 10, 15 to our database, but also I probably want to add 15, 10. The reason being that we want to eventually have some sort of connections database for first degree connections, and we want to be able to shard that by user ID. And so ultimately we're going to have to add both of those rows so that they can go in both of the appropriate shards. So in order to avoid having to make two writes at once and do a two-phase commit, we can put it in Kafka once, we can receive it in some stateless consumer right over here, and then we can split that write into two. Now because this thing is in Kafka, it means that the message is replayable, we're not going to lose it, and so this is going to make our thing a lot more fault tolerant, while basically ensuring that we have eventual consistency without requiring any two-phase commit or any Saga commit or anything like that. So now this is basically going to sync this message both to the partition that's responsible for handling connections for user 10 and the partition that's responsible for handling connections for user 15. We'll probably use some hash function to determine this in reality. So this is now going to flow through Kafka, and wouldn't you expect it, here it is, Flink. So what do we do on our Flink nodes? Well, basically we have a running tally of all of that user's connections cached in memory. And that's not going to be a lot of data, because at the end of the day, it's going to be like a 500 element list or something like that, which is not a lot. So in this case, user 10, we're adding element 15 to it. And in the case of user 15, we've just connected and now added element 10 to the end of our list. So now we have to go ahead and do the following. We want to modify all of our mutual connection databases so that we can quickly update all of our users' mutual connections. So for user 10, what's happening? Well, basically, if user 10 and user 15 were already mutual connections of one another, we basically want to be able to ensure that they are no longer mutual connections. Same thing with user 15. Like I mentioned, we need to do this twice for both of those because at the end of the day, we're basically keeping track of this for all users, and so we need to remove them as mutual connections of one another. Now, note that user 3 was already connected to user 10, which means that user 15 was incoming, is now a mutual connection of it, right? Because it goes 3 to 10, these guys are connected, and now we also have 15, which is also connected to it. So that's why we insert 3, 15. Like I said, everything is symmetric here. We also have to insert 15, 3. Note that user 4 was also connected with user 10. So now I have to insert 4, 15, insert 15, 4. And then on the other side of this, note that 8 was connected to user 15, which means that 8 and 10 are now mutual connections, and 10 and 8 are symmetric right. So all in all, basically this is on the order of O of m plus n writes. So keep in mind that because m and n are basically the number of connections that each of the two newly connected users have, this means that basically we're probably going to have 1,000 or a couple thousand writes every single time two users connect. Now that's a lot, but at the end of the day, it is feasible, right? We see Twitter do this for its fan out on tweets all the time. It's not unreasonable to actually make 1,000 writes per connection because it's all being done asynchronously in the background and no one's waiting on this. We can basically do it pretty slowly and we can afford to do so. That's totally fine. Of course, all of these writes are going to go through a load balancer, which is probably listening to Zookeeper somewhere, letting everyone know what databases handle what key range, right? User ID, X to Y or something like that. And then, of course, that way we can send the writes to the correct place. Cool. Now let's go ahead and talk about profile updates. So like I mentioned, we basically denormalized all of our data. So it's not really good enough to just have user IDs available because, as I mentioned, we would have to fetch all of their profiles every time we were doing a read. And so we opt to denormalize instead because we want to avoid this scatter-gather query. So the question is, basically, for connections, what we've done is we've taken new connections, we've put them in Flink, and then we've fanned them out to the database node that they need to go to. So again, we're doing m plus n writes, where m and n are the number of connections that each of those two newly connected users have. The problem is, for mutual connections, right, because when someone updates their profile, they basically have a bunch of mutual connections, right? We said on average around 25,000. So if a user has n connections, really they're going to have n times probably n connections, so n squared, but the reality is just, they have however many mutual connections that they do based on the connection graph. So around 25,000 writes. Now, a couple thousand was okay. I think 25,000, it starts to get pretty excessive, and it's probably not so feasible. Especially for people who have a lot more than 25,000 mutual connections, this is really starting to be overkill. So it's probably going to be too expensive to do a fan out of all of our profile updates to all three, not just all three, but all partitions of these mutual connection databases over on our left. So what can we do instead? Well, this is where some of our capacity estimates are going to come in. So like I mentioned, recall there's 1 billion people who use our service. They all update their profile once a year, so that means on average, there's probably going to be around 3 million profile updates per day, each of them with size 1 kilobyte that we have to store in our mutual connection databases. Cool. So basically the gist is, this is equal to 3 gigabytes of memory, which is not actually so much when you think about it. It's pretty reasonable. So what we want to do instead is, rather than basically fanning out all of our writes the second that they're made, we can actually batch them together, right? We can cache this in memory on a few servers. And then eventually, we'll go into this in the next slide, but we can upload them in a batch to all of our mutual connection databases. So let's say I make a write to my profile database. I've just changed something. Of course, we can use derived data, Kafka over here, and then sync it, all of our changes for the day, into memory, because it's only 3 gigabytes. That is very handleable. So these are our profile change caches. What are we actually going to do with those? Well, we can use a batch job. So the gist is, once per day, we have 3 gigabytes of data that we need to send over to all of our database instances and say, hey, you now have to update all of your denormalized data to reflect these profile changes. So we can basically run some sort of script, a batch job, a cron job, anything like that. And the gist is, because all of this data is cached in memory, it should be fairly easy to basically convert it into a format that we can easily upload to our database. Cool. So basically, any of these mutual connection databases, either via a stored procedure or via a script, can fetch all of the profile changes very quickly and update their relevant rows. Cool. Another thing that would be nice is that we don't actually need to lock all of our rows in our mutual connections table over here. The reason being that you only really need to lock all of your rows when you're making a batch insertion if you care about making consistent reads, meaning that you want to see the database in a consistent state and not between a transaction. But we don't really care about that, right? It's fine if I basically have some of my writes that are completed, others that are not, and then a user happens to search in between them. You can just grab the lock for the row that you're editing at a time. Not a huge deal. So what does this actually look like in reality? Well, let's say we have some mutuals table, right? We've got user 4 over here, and his mutuals are Donald Trump and Joe Biden. And you've got user 6, who has the mutuals of Donald Trump and Barack Obama. So you can see that Donald Trump is repeated, but the point is we're only going to send the Donald Trump row from our cache over to the database once, and then we'll do something like a hash join, where basically you would make a hash table indexed on the user ID of Donald Trump. And that way you can do one linear scan through this database, look if there's any data that needs to be replaced, and replace it accordingly. So as you can see, Joe Biden is going to replace this one row over here. Donald Trump is going to replace these 2 rows over here. And by doing this once a day, we can basically ensure that we're not making thousands of writes, we're just making one really big batch write at the end of the day to all of our partitions. And since this cache is relatively small, we can basically just broadcast all of that data over to the database. It's not like it has to be done in a particular way. We don't have to shard anything super fancy. We can basically just do this incrementally on some sort of schedule. Okay, let us go ahead and tie everything together. So on our left, we have a client. I already went through what happens when a client makes a new connection, but let's go ahead and get started over here. So when a client makes a new connection, the first thing that we can do is put that connection in Kafka. The reason is we just want to put it in there once so we don't have to do a 2-phase commit. We then have a stateless consumer, right? It doesn't need to maintain any state, so it doesn't have to be Flink or anything like that. It can be any old server that just listens to Kafka. All it's going to do is see a message like 10 to 15, send it into the queue for both 10, and send it into the queue for both 15. So let's say this is the queue for user 10, this is the queue for user 15. This is the case because we shard on the hash of our user ID. We can use something like consistent hashing to make sure that the load on all these queues should be relatively even. From there, we have Flink. Flink is basically going to maintain a mapping, from user to connections. The reason that we want to maintain this mapping from a user to their connections is so that when we see an incoming connection, we can very quickly find out who all of their new mutual connections are. So now we have a bunch of different operations, right? We've just figured out, hey, both of these guys have a bunch of new mutual connections. Let's go ahead and put those in our mutual connection database, which of course is going to be both sharded and indexed on our user ID, so that if I want to say find all of my mutual connections, or find all of user 4's mutual connections, I can do so very easily, and I only have to read from one single node. Great. Now let's go ahead and talk about the profile editing service, because since we've denormalized all of this data, we have to go ahead and figure out how we can update those profiles on some sort of interval. Like I mentioned, fan out is probably going to be too expensive here. It's just going to lead to too many writes, because we basically have to do a write per mutual connection every time you update your profile, which is infeasible. Instead, we're better off doing this in a batch. So we do our profile edit over here at the profile edit service. That's going to go into the profile database because ultimately we do need to store this somewhere. The profile database will probably have a more complete model of the profile where it's not just your school and your current employer, but all of your past employers, maybe some image data about you, something like that. I think MySQL should be pretty sufficient here because we mostly care about our read speeds. We're not writing to this table nearly as often. And by sharding and indexing on user ID, we can make sure that these guys have a fairly even distribution of writes, and same goes for reads. Cool. Then we go ahead and use change data capture to sync those updates into Kafka, and furthermore, cache them all in our profile edit caches. Then, using some sort of daily batch job, whether it is basically a stored procedure on all of these databases on the right, or just these guys directly querying to the databases via some sort of cron job, we can go ahead and push all of the data right to the databases and update them in place. this is going to be really useful because then when we do eventually hit our mutual search service, sure, we have eventual consistency as far as the profile updates go, but I'd say 99% of the time, if not more, you're going to see up-to-date data. The way that we would go ahead and fetch our data for our mutual search service is say, let's say we want to see it for user 4. That's going to hit our load balancer over here. It's going to route us to the correct database node. We're going to run our query on this particular node, and then of course we're going to return all of our data right here and back to our user. Well guys, I hope you found this video to be useful and informative. I think the trick with the batch update on the mutual connection databases was pretty cool. We haven't really gotten to see something like that used before. But when there are small enough deltas for your updates, you can actually do that option. Not everything has to be done streaming. Sometimes streaming is too expensive and you have to resort to using a batch job. Anyways, hope you have a great day, and I will see you in the next one.